All right, so far we know about digital, some of the digital basics like the logic gate, right, and also the number system. So by now probably you realize that almost all the digital circuit works only on two logic, just logic 0 and logic 1, right? Even in the lab you probably have seen that the only thing that matters to us is whether any point in the circuit is logic 0 or logic 1, right? So this concept is actually called Boolean concept, meaning anything is determined only by two logic, okay? Now, in addition to whatever you have seen in the circuit, all the um, Boolean components and Boolean ideas that we have seen in the digital circuit class can also be done in paper, just like math. Remember the very first lab, we actually tried the number system, right? And the binary numbers was one of the very important part of the number system, and we also tried some digital math with the binary number system, okay? One of the reasons we actually emphasize so much on the binary numbers because the digital circuit has a strong connection with the binary numbers, and the binary operations. It actually also works like the binary, operations. Okay, so meaning everything single thing that you are doing in your circuit is also doable in paper. That's very interesting because I'm sure that you have not seen this in any other you know, capacity in electric circuit. So this is something which is very special to digital circuit and digital world. All right, so let's start with some concept which will help you to understand the idea of the Boolean algebra and also some of the basics about the digital circuit and how you will see that the digital circuit can be strongly connected with the Boolean algebra and the Boolean math. Now in the Boolean algebra, just like your traditional algebra, we have variables, right? In the algebra, you have variables, right? Now, how do you represent variables? You use some symbol, right? Let's say for an example, in your math class, you use some symbol, right? X, Y, Z, or A, B, C, D, some variables, right? Similarly, in the Boolean algebra, we have symbol to represent the action, condition, or data. Now, again, as you can guess, any symbol that you represent in the Boolean algebra can have only two values, 0 and 1, which makes it a little bit easier to understand, right? Because if I just say, okay, I have a variable a, which is a Boolean variable, it can take either 0 or 1. That means its value will be 0 or 1, nothing else. So similar to any variable, you can also write a complement of variable. Okay. Now for an example, if a is a variable, you can also write a complement of variable like this. For an example, if this is your variable, you can also write a bar or a prime to make it complement. Now what do I mean by the complement? By complement, I actually means the reverse logic, because see, everything has a reverse logic, right? Like if a equals to 0, then a prime equals to 1. That's what I'm saying. If a equals to 1, then a prime equals to 0. Okay. Now in literature, sometimes we use a bar, sometimes we use a prime. You see this symbol? Okay, that's called prime in Boolean algebra. Now in pause, we use primes, as you already have seen, because we cannot draw the bars on top of the expressions. But no matter whether we use the bar or primes, the meaning is still same. And you can probably connect this with the inverter, because you have seen in the inverter just does the work, the reverse the logic, right? Opposite, make it opposite. So it's pretty similar in the Boolean algebra. Now you also have something called literal, meaning any variable or its complement is called literal. Okay, meaning if the b is a variable, b itself is also a literal, or b prime is a literal also. Okay, for an example, I tried to make it a little bit easier. When you do Boolean algebra, if b is a Boolean variable, remember any variable we write in this lecture and onward is all Boolean variables. That means those can take only 0 and 1, nothing else, right? So basically, if b equals to 0, automatically b prime equals to 1, right? Because that's the complement of b. If c equals to 1, then c prime should be 0. And if d equals to 1, then the double prime will be also 1, right? Now, why the double prime is 1? Because think about the double prime. You are actually flipping it twice, right? If you flip something twice, it will go back to the same position, right? Because you just have two logic, nothing else. If d equals to 0, if you do just d prime, it will be 1. And then you do again another prime, it will be 0, right? Because you keep flipping between two logic, right? So if the originally d equals to 1, and if you flip it twice, it will be 1 again, right? Just like that. So double prime is also possible, right? You can just write double prime in case if you need it. Now, I think we already have seen the binary addition, which will help you understand a little bit here, and also logic gates that will also help. Now, in Boolean algebra, addition is actually equivalent to OR gate, OR operation. Let's recall the OR gate. What the OR gate used to do? OR gate gives you high when any of the input is high, right? Or both of the inputs are high, right? The idea of addition is exactly the same. That's why the OR gate and the addition is actually equivalent. So remember, at the beginning of this lecture, I was just telling that everything that you do in your circuit, that you build or that you run, also doable in the paper just as Boolean math, okay? Which is really the powerful side of digital algebra, because instead of just drawing the circuit, you can basically write the equation for every circuit, and we'll learn, we'll talk about that, and we'll get up, up to that point where actually we do it. We'll even look at a couple of small ones today. Now, so the sum term is 1 if 1 and more is literal. So it's basically just the OR gate, and we'll show you some more examples. So let's say, to make it understandable, what we did is I wrote an expression. This is called Boolean expression, when you have some Boolean variables, okay? And then some Boolean operators. Now, what are the operators? That's a plus is operator, right? Because we're talking about the addition. So Boolean addition, Boolean is an operation. Now the prime, this is actually prime, right? I wrote bar, but it's prime, right? Prime or bar, this is also an operator, okay? All these are different kind of operator we can apply on Boolean variables. So if somebody gives you this expression and tells, okay, how about if I have a prime plus b plus c prime equals to 0? Can you guess what will be the values of a, b, and c? It's actually very easy to guess, because if you add 3 literal and then your sum is 0, that means all of these 3 literal individually must be 0, because there is no way you can get 0 in OR gate. Let's recall the OR gate. How you get 0 in the OR gate? You get 0 in the OR gate when everything is 0, right? Meaning both of the inputs are 0, right? Now we are talking about 3 input maybe here, but it's all zeros, okay? Now that means this. Each literal must be 0. Now, let's look at the first literal. The first literal is what? A prime, right? Or a bar. Now, if a prime is 0, that means what? A is 1, right? A prime is 0 means what? A is 1, prime and A is complement of each other, right? So that's why we wrote A equals to 1. Now, as you can guess, B equals to 0. And the C prime is also 0. That means C equals to 1, right? The prime of anything is 0 means what? Remember the first slide? If a prime and the variable itself are complement of each other, right? So from here, we can directly guess that A is 1, B equals to 0, and C equals to 1. And this is the only combination of A, B, and C which will make this expression 0. There is no way you can make it 0 except this combination, because everything else will make it 1. So, again, just to help a little bit. And Boolean multiplication, look at this. This is an algebra. So that's why we are talking about the variables. We are also talking about the operator, right? See, we already talked about 2 operators. The first one was complement. Second one is the addition. Third one is Boolean multiplication. Boolean multiplication, interestingly, is equivalent to AND gate or AND operation. Remember, what is the basic of AND gate? What does it do? AND gate gives you high only when all the inputs are high, right? That's the only time it gives you high, nothing, otherwise it gives you 0. Similarly, in Boolean multiplication gives you high when all of the variables are high, and that's it. So basically, if you just tell me this, that if you give this a dot b prime dot c prime, now remember this dot stands for Boolean multiplication, which also equivalent to AND operation, okay? Now, if somebody gives me this and said, oh, this is 1, that means all of these literals, there are 3 literals here, right? A is a literal, right? B prime is a literal, C prime another literal. All of these 3 literal must be high to make it high, because that's the only way AND gate gives you high, because if AND gate is high, that means every single thing must be high. Now, you can guess, if A equals to high, that means A equals to 1. But if B prime equals to high, that means B equals to what? 0, right? If C prime equals to high, meaning 1, that means C equals to 0, because the complement, So, again, it's just to give you an idea, but let's try some real expression and see whether we can evaluate this expression, okay? Now, instead of writing the variables, I just wrote the values, like zeros and ones, okay? And again, if you remember, when we talked about the logic gates, we said that there are only 3 basic gates: inverter, AND gate, and OR gate. Remember? This is actually the reason why we just have 3 basic gates. There are plenty of other gates, right? We have NAND gate, NOR gate, exclusive OR gates, exclusive NOR gates. There are several other gates, but these are the only 3 gates which are basic, because these are the gates which actually determines all the operator you have in Boolean algebra. You see, we just have 3 operator, right? Complement, addition, multiplication, and that's it. These are the only 3 operations you need in the Boolean algebra, nothing else. In the traditional algebra, we have more than this, right? We have several other operator. We have square root, square root, cubic root kind of things, or we have powers, right? It's also power. We have several other operator that we apply on the on the traditional algebra. In the Boolean algebra, it's a little bit easier because we just have 3 operators. Now, I applied some of the operator in some of these places, and we'll try to evaluate this expression. Now, remember, any Boolean expression, if you evaluate, at the end, you will again get either 0 or 1, right? Which also makes it easy. Okay, let's try to evaluate it. So what I did is, during this evaluation, I actually underlined in different places just to show you which part I'm looking at right now, okay? So you don't have to underline it. You can, of course, cannot underline in pause, but you don't even have to underline when you're doing in paper. It's just to make it easy. I just tried to underline it later. So I underlined here, so that means 0 prime. What will be the 0 prime? It will be 1, right? Because anything, if you just prime it, meaning take the complement, it will be just the other logic, right? So 0 prime becomes 1, right? Let's look at the next part. Now, as you can guess, we always take a look, we always give the higher precedence on anything you have inside the parenthesis, right? So basically, since there is a parenthesis here, what does it mean? That you actually have to do the operation that you have inside the parenthesis first, and then you will apply that prime, right? Because the prime is actually applied on the whole thing, right? So this is just like our basic, algebra. So 1.0, what does it mean? Let's recall, what is dot? Boolean multiplication. That means AND gate, right? Meaning AND operation, right? No. In the digital world, there is nothing like 1.0, right? It's always 1 and 0, right? It cannot be anything else. There is no fraction, right? This is 1.0, okay? Now again, what is dot? Multiplication, right? Which means AND operation. Now tell me, what will be the outcome of the AND operation when you have 1 and 0 in the input? It will be 0, right? Because the AND gate gives you high only when everything is high. So right now we don't have everything high, right? 1 and 0, so there are 2 different logic. So the output will be 0, right? So here we go. The output is 0, but we still have to deal with the prime here, right? 0 prime again makes it what? 1. 0 prime makes it 1. Now I have 1 plus 1, which means 1 or 1, right? Because the plus is or, right? Now, what will you will get in the OR gate if you do 1 plus 1? What will be the output of the OR operation? What will be the output of OR operation if you have both inputs are 1? It will be 1, right? So that's why 1 plus 1 will give you actually 1. This is interesting because this is not the tradition, the basic math. Because if you're doing the math, you just write what? 1 plus 1 is 2, right? But we're just dealing with the logic, not the numbers. So 1 plus 1 means once because of the OR gate. Because OR gate gives you high when both of the inputs are high, and this plus means OR operation, right? So again, if I evaluate the expression that was given to me, my answer is 1. Hi. Dot is AND, yeah. Dot is AND operation, which is again Boolean multiplication. Probably, most of the time we'll call it addition and multiplication. But again, inherently addition means OR operation, multiplication means AND operation. Even the prime means NOT gate, right? Inverter. So as you can see, pretty much all of these are can be implemented using just the gates, right? Okay, now let's look at another expression. Now this time, in my expression, we have variables. So instead of putting the raw values, we use the variables. Now before I start this time, let me remind one thing. Just like the traditional algebra, we do not put the dot, right? Remember when you write x, y in the algebra, what does it mean? X times y, right? But we do not write x dot y because there is a dot, but we don't write it, right? I'm saying we assume that there is a dot. Similarly, in the Boolean algebra, we also do not write dot. I just showed you the dot until this point because we are just beginning. I just wanted to make sure that you see the dots. But there are dots, like there are multiplications, which we do not write. For an example, look at this one, BC. That means this is actually B dot C. Okay, meaning B multiplication C, right? Again, this is Boolean multiplication, but we will not write the dot here. Okay, we'll probably write the dot when we play with the variables. I'm saying play with the raw values, but not with the variables. Now, this is my expression that is given to me, and as you can see in my expression, I have 3 variables, right? A, B, and C, right? And all these variables were given the values in the question. See, we say, the question said A equals to 0, B equals to 0, C equals to 0. So this is given to us, okay? Now, can you evaluate this expression? How do you evaluate the expression? The very first step is you replace the variable by their value, right? So I replaced it. Look at this, I replaced all of the, 3 variables by their values, right? And this time I used dot. The reason I used dot, just to make it a little bit clarified, because if I just use 0, 0, you'll be confused, right? This actually means 0 dot 0, which means B dot C, right? So I plugged all the values of A, B, and C. Now let's evaluate the expression. Now again, this evaluation is pretty similar to the last one, because as long as you have all the raw numbers, it's pretty same. Okay, now which one we'll deal with first? Probably 0 dot 0 here, okay? That will be what, 0, right? And AND operation, 0 and 0 makes it 0, right? And here inside this parenthesis, 0 prime is what, 1? And again 0 prime is 1, right? So again, let's look at the parenthesis here. This is 0 plus 0, and now here 1 plus 1. So 0 plus 0 makes it what, 0, right? There is a prime outside of the parenthesis. So this 0 prime makes it 1, right? Now I have 1 dot 1, which will be 1, right? Boolean multiplication and operation, 1. There is a prime outside, so 1 prime is 0. It's actually very simple if you just do it step by step. So in the Boolean algebra, if you are given an expression, if you know the values of the variables, all you have to do is just plug the values, you will find the answer. And it's always easy because your answer will be either 0 or 1, right? So if you understand up to this point, you actually should be ready for the very first 3 quizzes of chapter 4. We just started chapter 4, and It will be a long chapter, so we'll not be able to finish everything one lecture, okay? But we'll be doing more step, a couple of more ones today, and then we'll stop at some point. Now, let's look at some real example of how the Boolean expression is related to the digital circuit, or meaning the binary numbers or digital logics, okay? Now, let's say I have, can I write down the output column of the truth table below for the Boolean expression b prime plus a prime plus c? Now, all these variables are Boolean variables, right? And as I said, all these expressions are equivalent to a real circuit. That means after some point, once you are given the expression, you should be able to draw the circuit for the expression, because for every circuit we actually can write an expression, Boolean expression, and that's actually very straight. Now, let's see whether we understand how to draw the truth table from an expression. Now, at this point, we are trying to draw a truth table. Now, let's first look at the variables. How many variables I have here? 3, right? Any confusion? It's just A, B, and C, right? Now, for 3 variables, I already have drawn a truth table. I don't know the column X because I actually have to find the column X. But I already know the A, B, C. How do I know it? What I did is I actually wrote all the combinations of A, B, and C. You might be wondering, how did I know it so quick? There are plenty of different ways you can find the combination. So, first of all, let me give you a very simple formula. When you have 3 variables, how many rows you will have with the combination? It is actually very simple. No, I'm not talking about the column, the rows. This is a row, right? This is 1 row. This is my second row, okay? I'm talking about the row. That means how many combination of ABC you will have. There is a very simple formula. This is the way we actually deal with it. If you have 3 variable, it will be just 2 to the power 3, which is 8. I have 8 rows here, right? If you have 4 variables, it will be 2 to the power 4, which is 16, right? So that means it will be always 2 to the power number of variables. That means if you have 5 variables, how many rows you will have? 32. It's actually hugely exponential. If you have 6 variables, it will be 64, 2 to the power 6, okay? Now, I have actually 8 rows, I already know it, but how did I find these numbers? Now remember, if you look at the row, you will see that every row is different, right? And these are the all different combination. There is no other combination except this 8 row, okay? Now how did I find this? There is a very easy trick. Let me show you the trick. If you look at this row carefully, let's look at the row. Look at the first row, what is it? 0, 0, 0, which is binary 0, right? What is this one? 0, 0, 1. It's binary 1, right? What is the next one? 0, 1, 0. This is binary 2. What is the next one? 0, 1, 1, right? Binary 3. 1, 0, 0. Binary 4. 1, 0, 1. Binary 5. 1, 1, 0. Binary 6. And 1, 1, 1. That is binary 7. So all I did is just write 0 to 7 in binary. That's it. It's actually very simple if you just think like this. Some people even try it in a different manner. I'll show you that also. But most of the time what you do is, if you have to write 8 row, all you have to do is just write 0 to 7 in binary. That's it. If you have to write 16 rows, think about 2 to the 4, then it will be 16 rows, right? All you have to do is just write binary 0 to binary 15, okay? Because the maximum number you can write using 3-bit is 7, and that you actually have written here, right? After 7, you cannot write anything in 3-digit. You have to use 4-digit. That's what I'm saying. So, yeah. And same is true for 15. After 15, you cannot write anything in 4-digit. It has to be 5-digit. So, that's the max we can write in. Yeah, so that's why we go all the way up to 7, 0 to 7. Now, some people also try these. They do this. Let me show you that. If you look at the very rightmost column, you see that 0 and 1 are flipping in every column, right? Every row, right? You see? 0, 1, 0, 1, 0, 1. It's actually flipping every time, right? Now, if you go to the next column in the middle, it's actually flipping every other time. Look at this. 0, 0, then 1, 1. then 0 0 and 1 1, right? If you go to the very left one, it will be 4 0 4 1, right? So there is a pattern. If you go even left one, the next one, if you have 4 column, let's say, if you have to go to the next one, then there will be what, 16 row, right? So you'll see the first 8 is 0, next 8 is 1. Again, it's up to you which one you want. But most of the time, I prefer the binary numbers. Instead of thinking anything, I just write the binary numbers. So I already know what will be the combination of A, B, and C. Now, all I have to do when I have to write it, I have to draw my truth table. All I have to actually write is the last column, because that is the column which determines the expression, right? Which is the output column, which will be different between expression to expression, right? Now, let's look at our expression. This is given to us, right? B prime plus A prime C. Now, how do I know which row will have what? I actually have to do a separate calculation for each row. So this is how I do the calculation. So let's do it for row 1. What I do is this. I write the expression here. What are my values of A, B, C in row 1? All zeros, right? Look at the value. A is 0, B is 0, C is also 0. So all I did is here I plugged all 0 for A, B, and C. And then I evaluated the expression. I know how to evaluate it, right? We already tried it. So once you evaluate it, it's a 0 prime, that makes it 1. 0 prime here, that makes it 1. 1 dot 0, AND operation, gives you 0. And then 1 plus 0, this is an OR operation, gives you high. And that's why I actually wrote the blue one here, right? Because once I evaluate it, I know that this row will have 1 at the output. Okay? Let's do the same for row 2. Now this time, my inputs are a little bit different. My A equals to 0, B equals to 0, but C equals to 1, right? And that's exactly what I plugged. Look at this. I plugged C equals to 1 this time, right? And I did the evaluation, and at the end, I again got 1. So my rightmost column, which is my output column, is 1, right? So I can do I can do the same calculation for every single row, right? And that's exactly how I find what will be my column X for any expression. So basically that means for every expression, you can actually draw a truth table, right? In PAUSE, whenever you'll be doing some such question, you'll be actually given the truth table except the column X. In your answer, all you have to do is just write the column X in sequence. Be careful, in sequence, okay? Now, because the column X is the one, that is the one which actually matters, because other one I know actually 0 to 7, right? That's the same, for every combination of A, B, and C. So I actually tried a couple of more rows here. This is my row 3. Look at my input right now. For my row 3, the inputs are different, right? My A equals to 0, B equals to 1, C equals to 0, right? That's the same thing that I plugged here. See, B equals to 1, A and C is a 0. Once I evaluate it, I got 0. So I plugged 0 there in the column X. So you can do the same for all the rows. So I just, tried row up to row 3, but you can do all the rows for, using the same expression. So if you're up to this point, you should be ready for the next quiz, which is quiz 4. So we actually were trying to talk about these quizzes, and then once we do the quiz, you can get back to this lecture and look at these examples again. Now let's try to write a Boolean expression from the truth table. Remember, we just did the reverse process, right? Meaning, we are given the expression and then we found the column X. Now what happens if I'm given the truth table and then I have to find the expression? This is very interesting, because your expression, for every expression you can draw a truth table. For every truth table, you have an expression, right? So how do I find the expression from here? Now look at the truth table. Now this time my truth table is complete, right? My X column is also given because it's complete truth table. Now I have to write a Boolean expression from out of this, right? How can I write this? So the step is, in the Boolean, in the column X, what I look at is, this is my first step, step 1. I mark all the rows with 1 at the output. Let's look at my truth table. Can you tell me which rows I have 1 at the output? I actually marked those blue. Row number 2, right? This is my row number 2, right? row number 4 and row number 6, right? So what I did is in the step 1, I actually marked those 3 row, right? You see, again, based on your truth table, it might be more than 3, it might be more less than 3, it depends, right? So all you have to do is you have to mark those rows, identify those rows. We identified the rows for row 2, row 4 and row 6. That's the step 1, very simple. Now step 2, I'll be writing an expression for all these rows that I marked already. How do I write this expression? Let's look at, it's actually very simple. Let's look at how do I write the expression. Let's look at the row 2. If the value of A is 0, that means you have to write A prime. If the value is 1, you have to write A, okay? Now for an example, for the row 2, my expression would be A prime, B prime, C. Why? Because A equals to 0, B equals to 0, and C equals to 1. Anything is 1, it will be just the variable, okay? If anything is 0, it will be the prime, like a complement of that. So for my row 2, my expression is A prime, B prime, C. For my row 4, my expression is A prime, B, C. That's what I'm saying. It's actually very easy to read. For my row 6, my expression will be A, B prime, C, right? Based on just ones and zeros. And that's all I did here. For row 2, row 4, and row 6, I wrote the expression. Okay? If it is 0, we'll be writing the expression as a product, like multiplied with each other, and then we'll be using those complement if it is 0, using the variable if it is just 1. So I actually wrote one expression for each row that I marked. Other row, I don't care. I'll just write the expression for the rows. Those I already marked, right? So I wrote an expression for row 2, I wrote an expression for row 4, I wrote an expression for row 6. Any question? Okay, that was my step 2. The step 3, all I did is just add these 3 expressions. Very simple. I already have 3 expressions for 3 row, right? I might have even more, I might have even less based on the truth table, right? I just have 3 expressions, I added those 3 and that's it. You are done. That means this is the expression for the truth table you are given. And then when I add these 3 expression, there is no ordering, okay? So don't get confused. So it doesn't mean that you have to write this one first and this one next and this one next. There is no ordering, so you can use any ordering. So if I write just like row 4 expression of row 4 first, and then row 2, and then row 6, it will still be correct. There is no problem, okay? So there is no ordering when you add those expressions. Any question? Okay, so if we understand up to this point, we actually should be ready for our next quiz of this chapter, which is chapter 4, quiz 5. Okay? I'll stop here for today, since we have already 5 quizzes. So, but remember, this will be a continuous lecture, okay? Because we'll be working on these quizzes so that we understand the materials that we need to understand for our next labs, and also to make some progress, okay? So that means that we stop here, it's like a pause for this class. Next class we'll again start from the next quiz, because we have plenty of quizzes in chapter 4. So because chapter 4 is a very huge chunk of the materials that we have for our syllabus. So you'll be, you'll see that there are plenty of quizzes. It's almost like, I think, as I guess, or I can remember, there are 26 quizzes from this chapter. It's only 5 here, okay? So there will be, plenty of lectures coming from chapter 4, and then we'll be working back and forth, because the lectures are designed so that we get some help from the lecture to the lab, okay? That's why you'll see that we'll be basically going back and forth between the chapters, okay? So basically at the middle of chapter 4, we'll jump into chapter 5 and then we'll again come back to chapter 4 just because we want to sync with the lab. Let me give a pause here so that you can work on these 5 quizzes, and then again next class will start from here.